Given two finite dimensional linear vector spaces r power n and r power m, and given two vectors u in r power n and v in r power m, the tensor product is a linear map denoted by v tensor u, defined such that it maps vectors in Rn onto v in Rm. Given a vector x in R power n, v tensor u takes x and gives me the vector x dot u v in R power m. And in general, linear maps in finite vector spaces can be viewed as a summation of a few of these tensor products. For example, let's think of a matrix that maps vectors in R3 into vectors in R3. For example, this matrix M that's defined by these three vectors, three row vectors A, B, and C. The matrix M, when multiplied by a vector X, we obtain a new vector with components A dot X, because we multiply A by X, so we get A dot X. And in the second component we get B dot X. The third component we get C dot X. And so we can then write mx as the sum of the three components along the three vectors e1, e2, and e3. So this component is along the vector e1, this component along the vector e2, and this component along the vector e3. Each of these is a tensor product that can be written as e1 tensor A multiplied by x, e2 tensor B multiplied by x, and e3 tensor C multiplied by x. The following are some of the properties of the tensor product operation. Using this definition, the student should attempt to prove these equivalent relationships. And basically they show that the tensor product operation is primarily a linear operation. Since the tensor product is a linear map, it has a matrix representation when we use a particular coordinate system. By writing the components of V and U and utilizing the linearity of the tensor product and the properties that we mentioned, that we showed in the previous slide, we see that the tensor product can be written using the components vi, uj, and a summation of different tensor products using ei tensor ej. To find the equivalent matrix representation, we are going to take this linear operator and multiply it by x. So we're going to represent x as the summation of xk ek, use the properties of the tensor product to obtain this relationship. And this this form implies that the matrix representation of V tensor U is given by this form, which basically is the Mij is equal to Vi Uj. The tensor product will be used to simplify many relationships that will be presented later in this course.